OJ-287, the extreme black hole system set to merge in 10,000 years. The intriguing black hole system OJ-287 has become even more captivating. Stay updated with the Starts with a Bang newsletter. Join Dr. Ethan Siegel on a cosmic journey as he tackles some of the universe's most profound questions. Black holes are everywhere in our universe. When two black holes collide, they can convert a remarkable amount of their mass into energy in the form of gravitational waves during a brief moment. Initially, these black holes orbit each other over much longer periods, often ranging from 1 to 10 years. Astronomers can utilize pulsar timing to detect these cumulative effects across the cosmos. Observing gravitational waves requires different types of detectors that are tailored to capture signals from various mass ranges. Most detected black holes are on the lighter side, typically weighing just a handful of solar masses. When an optical interferometer's two arms are equally long and undisturbed by gravitational waves, the resulting signal is stable, and the interference pattern remains unchanged. If a gravitational wave passes by, it alters the lengths of the arms, resulting in a real oscillating signal and a dynamic interference pattern that shifts with time. This innovative technique allows scientists to directly detect gravitational waves. However, there are supermassive black holes, which can be millions or even billions of solar masses situated within galaxies. There are three distinct methods to observe gravitational waves: ground-based laser interferometers, space-based laser interferometers, and pulsar timing arrays. Each technique is particularly sensitive to specific types of gravitational wave signals. LIGO, for instance, was the first to detect such waves at extraordinarily high frequencies, while the nanograv collaboration has gathered compelling evidence at much lower frequencies around the nanohertz range. Pulsar timing is particularly valuable for exploring the longest gravitational waves that arise from the heaviest pairs of supermassive black holes in orbit. Because these massive black holes are beyond the detection capabilities of LIGO, they necessitate the use of longer baseline gravitational wave observatories. The accompanying image showcases an illustration of the three planned LISA spacecraft, laser interferometer space antennae, that will orbit behind Earth. This mission represents our first foray into space-based gravitational wave detection, allowing us to observe objects that could be thousands of times more massive than what LIGO can currently detect. An array of LISA detectors, positioned at various locations in Earth's orbit, could potentially identify even merging supermassive black holes, an idea referred to as the Big Bang Observer. LISA, the suggested Big Bang Observer, and pulsar timing arrays could provide direct observations of these cosmic events. A visual representation illustrates how an array of pulsars being monitored could capture the gravitational wave signals while space-time is disturbed by these waves. The longest wavelength gravitational waves, such as those generated by the most massive pairs of merging black holes, can only be detected by techniques that take advantage of exceptionally long baselines, like pulsar timing arrays. Moreover, with a sufficiently accurate laser array, it's theoretically possible to detect the quantum characteristics of gravitational waves. Galactic collisions bring multiple supermassive black holes together, culminating in inspirals, mergers, and ringdowns. The chaotic nuclei of these colliding galaxies conceal the final phase of two merging galactic cores. The infrared images on the right highlight 5 galaxies, showing clear evidence of 2 distinct black holes in the galactic cores. Given enough time, these black holes will eventually merge, with the final moments dictated by gravitational wave emissions, until their event horizons touch and they become one. Among these systems, OJ-287 stands out as the heaviest binary supermassive black hole, first identified in 1887. OJ-287 represents the most massive known pair of black holes in the universe, with gravitational waves so long they remain undetectable by LISA. For this phenomenon, a longer baseline observatory for gravitational waves could be essential, as well as a sufficiently advanced pulsar timing array. Although OJ-287 was first recorded in 1887, understanding its nature and distance didn't come until the 1960s. Roughly 4 billion light-years from Earth, this system consists of two black holes, one weighing about 150 million solar masses, and the other approximately 18 billion solar masses. The infographic shows the relative sizes of the event horizons for the two orbiting supermassive black holes in the OJ-287 system. The larger black hole, approximately 18 billion solar masses, spans 12 times the distance of Neptune's orbit, whereas the smaller one, around 150 million solar masses, is similar to the orbit of Ceres around the Sun. The known heaviest black hole surpasses OJ-287's primary mass by a slight margin. These black holes complete an orbit every 11 to 12 years. The two peaks observed from OJ-287 correspond to the smaller black hole moving through the larger one's accretion disk twice during each orbit. This flaring rhythm, along with time-dependent variations in the flare's orientation, aligns perfectly with the predictions made by Einstein's general relativity. Thanks to the principles of general relativity, their orbits experience a notable precession of 39 degrees per revolution. An accompanying animation illustrates how a lower mass black hole penetrates the accretion disk surrounding a larger supermassive black hole. As the smaller black hole crosses through the disk, a bright flare occurs. Over extended periods, these black holes are destined to inspiral and merge, creating an enormous gravitational wave signature during the process. This distinctive double flare phenomenon is a hallmark of OJ-287. Flaring outbursts transpire when the less massive black hole breaches the accretion disk of the larger one. The left and right views reveal close-up and broader perspectives of the nucleus of the nearby galaxy NGC 7727, located merely 89 million light-years away. This galaxy is home to the closest known pair of binary supermassive black holes, which are separated by 1,600 light-years. While environmental friction might cause supermassive black holes to draw closer, gravitational wave emissions will primarily govern the final stages of their inspiral and eventual merger. Binary supermassive black holes are relatively common in galactic centers, appearing in about 1 in 1,000 galactic systems. This double quasar isn't a rare occurrence. It represents roughly 0.1% of all quasars. The presence of two supermassive black holes in orbit around one another not only affects nearby matter, but also leaves distinct traces in the electromagnetic radiation they emit. This radiation serves as a complementary signature to the gravitational waves and provides a valuable method for directly observing the black holes and independently confirming their masses. The radio data from the binary black hole system 3C344 exhibits physics similar to that of OJ-287. The space-based radioastron, when paired with ground-based telescopes, enables very long baseline interferometry, VLBI. In VLBI, the radio signals gathered from each telescope are recorded prior to being sent to a central facility. Each observation is time-stamped with a highly accurate, high-frequency atomic clock to ensure synchronization during analysis. The greater the distance between the individual telescopes, the higher the resolution that can be achieved. This technique provides our sharpest observations yet. A composite image capturing OJ-287 during an active flaring phase in both X-ray and radio wavelengths reveals the orbital trail, indicating the motion of the secondary black hole. This binary supermassive system comprises one component roughly 18 billion solar masses and another around 150 million solar masses. and their eventual merger is anticipated to emit a staggering amount of energy, especially in the form of gravitational waves, akin to that recorded in the most energetically injected galaxy cluster. A new, elongated ribbon-like radio jet has recently been identified, enhancing our understanding of OJ-287. This groundbreaking observation, made with the space-based radioastron telescope alongside a collaborative ground-based 27-element array, yields approximately 15 micro-arcsecond resolution of this distant black hole binary. The jet exhibits temperatures exceeding 10 to the 13 Kelvin, and its shape implies powerful magnetic fields near the more massive of the two black holes in orbit. In about 10,000 years, these black holes are expected to merge. The accompanying illustration highlights the various phases of a supermassive black hole merger, along with the anticipated signals that scientists believe will result as the event unfolds. Once the two merging black holes pass through the same event horizon, all gravitational wave emissions come to a halt, with only the ring-down phase remaining due to the changing shape of the post-merger event horizon. The merger is projected to release an astounding 3 × 10⁵ joules of gravitational wave energy, marking what would be an unprecedented cosmic event. What are your thoughts about the complexities surrounding black hole mergers? Do you believe we are adequately prepared to detect and interpret the signals they emit? Share your views in the comments section below. OJ-287, unveiling the secrets of a mysterious galaxy. What lies at the heart of a galaxy 5 billion light-years from Earth may change everything we know about the cosmos. OJ-277 has long been a source of intrigue and debate among astronomers. And with this groundbreaking new image, the mystery only deepens. For over a century and a half, scientists have been captivated by OJ-277's unpredictable flickering light. The leading theory? There aren't just one, but two supermassive black holes tangled together in a dramatic cosmic dance, possibly on the verge of merging. But here's where it gets truly fascinating. A team of international researchers, led by Dr. Efthalia Traianu from Heidelberg University, has now captured an unprecedented image of this enigmatic galaxy's core, peeling back the veil on phenomena we've never glimpsed before. Using a space-based radio telescope in tandem with a worldwide network of ground observatories, these scientists achieved a resolution so fine, it's as if they built a virtual telescope 5 Earths wide. The resulting image reveals a sharply twisted, ribbon-like segment of the plasma jet shooting from the heart of OJ-287. Why does this matter? Until now, such detail in this galaxy's jet, including its dramatic curve, was entirely unknown, offering new windows into the wildly extreme environment around supermassive black holes. OJ-287 falls into the blazar category, galaxies with actively feeding black holes that radiate staggering amounts of energy. As matter streams into the black hole, it's occasionally blasted outward at almost light speed in the form of a plasma jet, filled with searing heat, cosmic rays, heavy particles, and potent magnetic fields. Dr. Traianu, a leading member of the research team, emphasizes just how transformative this detailed view is. We have never before observed the structure in the OJ-287 galaxy at the level of detail seen in the new image. One dazzling detail. Some parts of the jet reach temperatures above 10 trillion Kelvin. That's nearly unimaginable, indicating titanic energy and motion just a hair's breadth from a black hole. The image even documented the birth, expansion, and sudden collision of a new shockwave within the plasma jet. A feature believed to result from a rare and powerful gamma-ray event glimpsed back in 2017, hinting at energies on the trillion electron-volt scale. How did they do it? The image was captured using interferometry, a technique that harnesses the wave nature of light. The Spectre-R satellite's 10-meter antenna, part of the Radio Astron mission, worked in concert with 27 ground-based radio observatories spread across the globe. By measuring the tiny differences in how radio waves arrive at each telescope, scientists stitched together even more. The new data sheds light on how their colossal gravitational poles twist, tilt, and sculpt the plasma jets they hurl into space. According to Dr. Trianu, its special properties make the galaxy an ideal candidate for further research into merging black holes and the associated gravitational waves. And this invites sharp debate. Could OJ-287 actually be the strongest evidence yet for merging supermassive black holes and, by extension, the source of future huge bursts of gravitational waves? Or is there another explanation altogether? What do you think? Does this astonishing image finally solve a cosmic riddle? Or does it raise even more questions about the volatile nature of galaxies? Could our understanding of black holes and their role in the universe be upended by discoveries yet to come? Share your thoughts below. Do you agree with the binary black hole theory, or are you skeptical? Let's hear your take.